In this video, we extend our model of the solid by including the periodic potential of the ions, introducing a displacement operator, solving for Bloch functions, and finally adding a periodic boundary condition. So, a better model than just a simple free electron gas is one that includes a periodic potential that is what the underlying ions, positive ions in the lattice would be. One example would be a localized atomic ground state, such as the one I've sketched out here, that is repeated with a period of repetition of A. But this is a simple one-dimensional lattice that has a specific potential, but it doesn't have to be this potential. Any potential can be treated exactly in the same way mathematically. So the only requirement you have is that the potential be periodic. That is, V of x plus A is identical to V of x. So if I look at any point here at x, when I add A over here, I'll have the same value of the potential. So the Hamiltonian then is simply minus h bar squared over 2m d squared by dx squared, so it's a one-dimensional problem, plus v of x, where v of x includes all the potentials that are repeated. We can now define an operator, d, called the displacement operator, which describes the translational symmetry of this potential. So if we take d and we apply it to a function f of x, we get f of x plus a. That's exactly what we see with the potential. So the solution to this kind of Hamiltonian must be an eigenfunction of the Hamiltonian, but we also have a question of how does it transform under the effect of the action of a displacement operator. So we'll see what happens with this by calculating the commutating relationship between the displacement operator and the Hamiltonian. So the commutator of d and h is just dh minus hd. Well, we can write that down relatively straightforwardly. So we take the commutator of d and h, apply it to f of x, and we get d, and then the Hamiltonian, which is minus h bar squared over 2m d squared by dx squared plus v of x, apply it to f of x. And then the second term is the same Hamiltonian first and then the d after. So now the first thing we can do is just apply d to f of x. When we apply d to f of x, it's going to give us f of x plus a. And here we're going to apply the Hamiltonian to f of x. Well, we know what that does too. So when we apply the Hamiltonian, we get minus h bar squared over 2m f double prime of x plus v of x times f of x. That's this first term. And this is all, you have d in the front. So d is going to be applied to the whole thing. And then you have minus the Hamiltonian and then f of x plus a because we've applied d to f of x. We can now take the first term again and now apply d. So now we get minus h bar squared over 2m f double prime of f of x plus a, because we've applied d, plus v of x plus a, because we've applied d, and f times f of x plus a. And the second term gives us minus h bar squared over 2m f double prime of x plus a, because that's just the second derivative with respect to x, plus v of x times f of x plus a. So these two, at first glance, don't look like they subtract out exactly. But you remember the potential is periodic. That is, v of x is equal to v of x plus a. So we can replace the v of x over here with v of x plus a. And now the two cancel completely. And that shows that the displacement operator and the Hamiltonian commute. That means we can have simultaneous eigenfunctions of both operators. Well, let's look at what the eigenfunction of a displacement operator might be. The eigenvalue equation for the displacement operator simply says that d applied to psi is equal to lambda times psi of x. So these two must be the same. Well, one way we can look at this is we know that when we apply d, we get psi of x plus a, and that must equal to lambda times psi of x. Well, lambda can't be 0, right? So it must be a complex number which can be expressed with a phasor, and a complex number that has a magnitude of 1. But it shifts the phase, and therefore can make this equality work. So let's imagine that lambda is just e to the I q times a. So this is a phase factor qa, magnitude of 1, so this remains normalized. And that means that we have a condition on the wave function in a periodic potential. So if you have a periodic potential which works with the displacement operator, that is, you can generate every point on the potential by applying the displacement operator, then psi of x plus a must simply be equal to e to the I qa times psi of x. That's a function that will now satisfy this eigenvalue equation. So this is called a Bloch function. And this is Bloch's theorem. And it makes sort of sense. It says that if you have a periodic lattice that goes to infinity, then the wave function at any point shifted by a had better be the same, because by symmetry you don't know where you are in the solid, because there's no endpoint, so you can't be close to the edge. And any place you are in the solid looks the same as long as you're in the same relative position compared to the origin, or a, or 2a, or so on. So Bloch's theorem only applies, as I said, to an infinitely repeating potential. But our goal is to model a macroscopic crystal, so it's not infinite. The number of repeating units is going to be on the order of 10 to the 10th or 10 to the 20th, on the order of Avogadro's numbers or so. If you assume that the edges of the solid are always far away, then you can apply Bloch's theorem. And if you apply periodic boundary conditions, then you can apply Bloch's theorem universally to models of solid. Because if you apply periodic boundary conditions, when we reach one end, it'll wrap around and go to the other end. And so periodic boundary conditions allow you to use the Bloch function to understand how electrons work in solids. So let's look at what the periodic boundary condition does. Let's imagine we have n is the number of atoms in the system. If you wrap the end of the potential back to the start to get a periodic boundary condition, that says that psi of x plus Na is equal to psi of x. That's exactly in the same position. But we know that every time we apply the displacement operator with the Bloch function, we get e to the I qa as a phase. So this is just applying the displacement operator n times, right? And so by Bloch's theorem, you get that e to the I nqa times psi of x has got to be equal to psi of x, right? Because it brings you back to the original position. Well, this puts a constraint on e to the I nqa. It says that e to the I nqa has to be equal to 1, which means that n times q times a has to be equal to 2 pi. This leads to quantization of the factor q, and actually it's equal to 2 pi times an integer n, right? And so that means that q is quantized. So this q is sort of like the wave number in the free electron gas model. Q is equal to 2 pi n over capital N times a, where n is 0, plus or minus 1, plus or minus 2, all the way to infinity.